Hello, and welcome to our presentation of a RAG approach for typological database completion. Here's the quick agenda for the presentation. I'll go over the motivation, I'll then describe our approach, and we'll look at the results, and we'll wrap it up with a conclusion and some potential follow-on work. Grambank is an online database of language features and contains information on more than 2,000 languages. The database is structured around 195 language features, describing things such as word order, verbal tense, and nominal plurals, among other features. Each feature is coded using specific instructions. They are typically phrased as questions about the grammatical structure of the language. For the most, they are binary yes-no questions, though there are a handful of multi-valued questions. The database is hand-coded by a team of contributors. When answering questions for a language, the coders provide a code value, a document source that was used to determine the answer, and a comment column for any comments. When providing a source reference, page numbers are also requested. While there are over 2,000 languages and 400,000 data points, there are still thousands of languages not covered. One of the goals of Grambank is to cover all languages that have a grammar book or other linguistic reference material. Questionnaires for a language are typically provided to a single contributor, and completing the remainder of the database may require significant human capital. Therefore, we ask, can we use these LLMs as a tool to assist with the expansion of coverage? In order to fill this gap, we propose a Retrieval Augmented Generation approach using a large language model that has access to linguistic reference material. Since the questionnaire is intended to be completed by non-experts using grammar books and sketches, a sufficiently capable LLM with access to the correct resources may be able to provide feature codes for languages not present in Grambank. Our approach uses a RAG vector database that is loaded with grammar books for languages. Filling out a feature value for a specified language involves two steps. First, relevant grammar book excerpts are extracted from the database using the feature question and description. And then second, the excerpts are provided to an LLM along with the feature description and coding instructions. The LLM then returns the coded value for that feature. And then we do this process for all the features for all the languages that we evaluated. So here's the same process, just shown pictorially this time. The top portion shows the initial steps of loading the database with the reference material. The documents are chunked into pages, and an embedding vector for each page is then stored in the database. We chose to use a single page as a chunk size because page numbers are the level of specificity that human coders use when filling out features, and this allows us to compare our results with the human coders. The bottom portion depicts how a single feature is coded. Again, the relevant excerpts are retrieved from the database and passed to the LLM, along with the question, description, and coding procedure. So the first basic question is whether RAG with grammar books improves the performance compared to just simply asking the LLM for an answer. So we created prompts that both did and did not contain the retrieved document pages from the database. Baseline values show the performance with no retrieved documents included, and then RAG values show the number of features correctly predicted when including the retrieved pages in the document, in the prompt. For all languages, RAG showed an improvement over the baseline with increases of 30% to 50%, indicating the effectiveness of this approach. So a natural extension would be to include more excerpts from grammar books to see if that further increases performance. And so for each language, we performed experiments that included an increasing number of pages in the prompt, up to 40. Our results show that performance increases as more documents are added, but it pretty quickly plateaus. So that was for the overall performance. But the individual system components, namely the RAG database and the LLM, are largely independent and their performance can be separately assessed. For RAG, we can analyze whether the system selects the same pages that the human coders used. So when the coders determine feature values, they are encouraged to include both the reference book and the page numbers used to determine the value. For the features that have page numbers identified, we can evaluate the similarity with the pages retrieved via vector search. The feature, which is expressed in the form of a question, is always included in the search term. We evaluated both including and omitting the summary in the search, shown in the with summary and without summary rows. For each feature, we calculate the similarity between the set of retrieved pages and the ground truth provided with Grambank. Within a language, we calculate the mean and maximum of all the similarity scores shown in the mean and max columns. As a coarser indication of similarity, we evaluate the number of features where at least one of the retrieved pages matches the ground truth, shown in the greater than 1 match column. Overall, the RAG approach shows a good deal of agreement between the database search and human coding, with more than 50% of features across all languages having at least one matching page. In general, including the summary and the prompt improves the similarity scores, although the mean similarity score is lower in Mizo when using the summary, and the number of features with at least one match is lower in Southern Jingpo. Natugu has the worst similarity scores among all the languages, but this may be attributed to it also having the most source documents. To evaluate how well the LLM uses the provided material to determine the feature value, we bypass the database search entirely and instead directly include the reference pages in the prompt to the LLM. As with the vector database characterization, we are only able to utilize this approach for features that have associated reference page numbers in the Grambank dataset. The skyline column shows the number of features correctly predicted. We also evaluate the full pipeline, right, the database and the LLM, on a set of features that have reference pages. Comparing to the Skyline approach, the full pipeline sometimes, but not always, outperforms Skyline. Natugu shows the largest increase from Skyline to the full pipeline. This may be attributed to the increased number of grammar sources, which could increase the amount of highly relevant excerpts included in the prompt, but this requires further exploration. Ultimately, utilizing linguistic reference material, such as grammar books, into RAG pipelines can yield useful benefits. While not a replacement for human coders, this approach could potentially be useful as a tool for linguists completing Grambank entries, either as a first draft or as a sounding board to compare your answers to. Follow-on work for this paper could include using newer LLMs, experimenting with additional languages, and exploring improvements to the grammar book vectorization. And a really useful extension would be answer verification, where like an LLM agent or critic could be set up to verify whether the answer is supported by the evidence. So it's kind of a check on the tool, and this would help progress trust in this approach. So that's it, and thank you for your time.